This video will introduce you to the basics of the rotational version of kinetic energy, work, and power. For starters, we're going to focus on kinetic energy. We learned in class that an object has kinetic energy when it's moving. So that means that something that's rotating must have some form of kinetic energy because clearly it's in motion. An object that is simply rotating, in other words, it's rotating in one spot where the axis of rotation is stationary, it has rotational kinetic energy. And something that is rolling has both rotational and what we call translational kinetic energy. Translational kinetic energy is basically a fancy name for saying the linear kinetic energy that we've studied in the past. When something is rolling, that means that its axis of rotation is moving in addition to it rotating. We know translational kinetic energy can be found using the equation 1/2 mass times velocity squared. Rotational kinetic energy is similar, except this time, instead of mass, we have its rotational equivalent, which we learned is the moment of inertia. And instead of a linear velocity squared, we have the angular velocity squared. Some other concepts that have used this rotational kinetic energy aspect is work. So when we were dealing with translational motion, otherwise known as linear motion, we learned that we could find work using two separate methods. One method was the definition for work, which was the force times the displacement times the cosine of the angle between the force and displacement vectors. We also learned that work was related to kinetic energy by the work kinetic energy theorem. When things are rotating, we have similar equations. We use the rotational equivalent of all of these variables. So instead of force, we have torque. And instead of a linear displacement, we have an angular displacement, theta. This time we don't use the cosine of the angle because torque and angular displacement will always be in the clockwise or counterclockwise directions. One thing that'll make this a little bit different than when we used work in the linear sense is if we have a clockwise torque, we'll plug in a negative number for the torque in this work equation. Similarly, if we have a clockwise displacement, angular displacement, we'll plug in a negative for that angular displacement. That means that if the torque and the angular displacement are in the same direction, either clockwise or counterclockwise, then we'll have positive work, which means we'll be adding energy into our system. We can also still use the work kinetic energy theorem, saying that the net work is the change in kinetic energy. However, if something is rotating, we would use the change in rotational kinetic energy rather than the change in translational kinetic energy. Finally, we're going to focus on power. Remember that power is the rate at which it's done, or the work, divided by time. That's the average power, and that equation is still true even if something is rotating. However, if we want the instantaneous power, we can plug in that equation, the rotational equation for work here, and we see that we could combine this angular displacement and time because angular displacement divided by time is equal to the average velocity. So I can find the power by multiplying the torque times the angular velocity as well. We'll practice using these equations with some practice problems in class.